Good afternoon. First start with what is Formula Student. Predominantly Formula Student is an international design competition. Every year the car will start from scratch. It's a new car every year which we design, develop and build. It is a Formula style single seat racer. It is not just build a fast car, it also incorporates business in the real world. So there are other things we have to consider, such as business, project management, team development, budgeting skills, which are all very applicable to the real world. This is our scenario in brief. So the idea is this car is one of 1,000. We build it as a prototype. It's got to be affordable. So it's got to be as a weekend racer worth roughly 25 to 30 grand. From this map, you'll be able to see it is a very internationally wide competition. There are teams from all over the world, mostly centred around Europe and North America. There are roughly about 500 teams, point-scoring teams from around the world, which just shows how diverse this competition is. Equally, there are competitions to go with that. There are quite a selection now, well, spread out throughout the world. So there's this Formula Student team, there is somewhere where they can compete with their car. This is LU Motorsport, so this is our senior team for this year, along with some newcomers for the intake this year who joined the team. The team is built up of predominantly undergraduates doing various degrees across the university. It's all done in our spare time, alongside doing our degrees. It is mainly student-led, and we're responsible for the management of the team. We design, manufacture and build these cars ourselves. We try and do as much as possible. So all the chassis will start from scratch, and we do it ourselves in our lab. We're able to shape and weld the tubes together. We're very proud of the car we produce. We all chip in. We have a lot of commitment goes into it, and at the end of the day I think everyone's very pleased with the result. These are our key team members, so these are head of the various areas of the car. Along with these people doing various degrees, they're also supported by the 20 other team members that range from being in their first year to their fourth year in their degree. Facilities that we have here and support. We're very lucky to have 24-hour access to a machine shop and a Formula Student workshop, as well as the department's test facilities. We get support mainly from ACME and the Wilson School, both technical and financial, and also from our faculty advisor, and of course we have academic support. Just quickly run through what a Formula Student event entails. So each event you will have static and dynamic events. So first, the static event is cost and sustainability. In this area, the idea is this car's got to be sellable for 25 to 30 grand. You've got to cost up the whole car. There'll be a value for every nut, bolt, washer, every part of the car, of how it's manufactured and how it's assembled. And this will give a total price for the car. Then have a business presentation, so we have those 1,000 units. We've got to justify how we're going to sell those 1,000 units. Is it going to be used to create a race series? Is it just going to sell the chassis? Followed by engineering design, which consists of industry experts. They'll look at the car, they'll scrutinise design, they'll want to know why you made this part out of this material, how strong it is. They'll want to know your engineering justifications and calculations. Move on to the dynamic bit that people prefer. Start with the skid pan. So this is a figure of 8. You'll do 2 laps, one each direction, and take the fastest lap. And obviously the idea is to go as fast as you can around this circle. Here you can see in the background there's a picture. This is in Germany. They like to make the track wet, just to make life slightly more difficult. It's followed by an acceleration run. So this is from standstill, 0 to 75 metres. And of course the fastest cars will travel that distance will gain the most points. It's followed by a sprint course. So this is roughly a kilometre long. This is Silverstone's course from last year. It's quite a tight, twisty track. And obviously the idea is to get around that as quick as possible. It's followed by an endurance and fuel efficiency. So they take this 1 kilometre track. You'll then have to do 22 kilometres instead of a kilometre. And this incorporates a driver change in the middle. As well as fuel economy now being a big factor. At the end, depending on how much fuel you use, will depend on your points, which is a big thing at the moment. It's trying to get the most power and use the least amount of fuel. So you've got to get that balance between lap times and fuel efficiency. These are the 3 events we intend to go to this year. So first of all, We're going to Silverstone in a week's time. This will be followed by going to Hockenheim in Germany, and then finally the Czech Republic in September. I'd now like to hand you over to Alan Tull, our Deputy Team Leader and Head of Chassis.
Thank you. Okay, good afternoon. I'm just going to give a quick overview of LFS15's design and the design process. So starting with the chassis, a number of aims were set, one which, obvious one really, is the reduction in mass. This was achieved by using, or the aim was to achieve this through the use of regulated members to support structural loads from subsystems such as drivetrain and suspension. There's also further aim to improve the packaging of subsystems such as electronics and aerodynamic components. Furthermore, the final aim was to simplify the design compared to previous years by reducing the use of regulated members, which could increase the overall chassis mass. The development of the chassis was backed up through the validation of the 1D FEA model that was used throughout the design process. This was an academic project which made use of the four-poster rig in the AAE department. This also considered the effect of the body panels on the stiffness of the chassis. So this resulted in the final design that had a mass of 24.7 kilograms, not including brackets. This was about approximately a 1 kilogram reduction over previous years. Torsional stiffness was retained at around 1900 Newton meters per degree. Also, LFS15 makes the most extensive use of structural composites in LUM vehicle. The design and development of these structures was also backed up through physical testing. So moving on to suspension. The aim here was to retain LFS14's kinematics. It was found that the handling of the 2014 vehicles are very favourable. However, issues were noted with the reliability of the system. Therefore, a further aim was to improve the overall reliability and maintainability of both the suspension and the uprights. The final aim was to implement anti-roll bars. So the final design, the suspension hard points were moved to better integrate it with the chassis and improve packaging. Additionally, a new anti-roll bar design was implemented that makes use of a blade type design. This allows for easy adjustments. Also, finally, a new rear upright design was manufactured. The aim of this was to reduce overall manufacturing costs and improve the maintainability of the upright. So moving on to engine development. Major targets here were to design and to improve the overall reliability of the engine, tune for fuel efficiency using lean mapping, and improve the overall drivability of the vehicle by moving peak power and peak torque to a lower speed. So these aims result in the following developments. A completely new intake has been designed. This was a smaller volume than previous intakes with the aim to enable it to improve the overall drivability. A new exhaust was also developed to conform to the new noise regulations brought in this year, and also to complement the new intake design. Improved throttle actuation design was also implemented. So after designing and manufacturing these components, they were taken onto the dyno power torque a few weeks ago to validate their performance. These are just a few images taken at dyno power torque. So moving on to aerodynamics, LFS14 was the first LU motorsport vehicle to include aerodynamics. Therefore, there were a number of different targets in this area. Firstly, on the simulation side, the aim was to validate 2D and 3D CFD that had been undertaken previously. This was through the use of wind tunnel and track testing. One of the key performance objectives was to develop the new wing designs using the same NACA profiles that were utilised on LFS14 to simplify and reduce manufacturing costs. The overall aim of the aerodynamic package this year was to retain the 2014 levels of downforce and drag with the new 2015 performance unit rules. So the development of the aerodynamic package was split into two areas. Initially, analysis was undertaken utilising 2D CFD. This was then complemented using wind tunnel testing to validate the final design. There was also different types of rear wing end plate were also considered during this testing. The final design of the wings is a triple element front and rear wing. They also have a carbon fibre reinforced polymer Nomex sandwich structure to reduce the overall mass. Finally, at the end of 2014, LFS15 was taken out to do some aerodynamic testing. The aims of this was to refine the overall aerodynamic setup, to validate the previously undertaken CFD, and also to perform flow visualization, as shown in the video on the right. I shall now hand you back to Jamie to conclude the presentation.
I'd like to take this opportunity to thank everyone who's helped us this year. We couldn't do it without you. Who's the technicians, university, students, academic staff, and our faculty advisor, and of course our sponsors. We're very thankful, and we appreciate your help and hopefully for your continued support in the future. I'd now like to invite the team to stand around the car as we unveil the car.